Ready? Welcome back to our weekly tapes on electrochemistry. Today we're going to finish up chapter 6, at least as much as we're going to talk about in this time, and we'll finish up by talking briefly about cyclic voltammetry. Before we left, we talked about linear sweep voltammetry, which we used a linearly varying potential versus time and applied that to our working electrode and then measured the current that flowed when we applied that potential. And let's just review that just for a minute. For LSV, as we called it, we apply potential versus time, and that's a linear function. And if we look at the current for linear sweep voltammetry versus time, we see that we got a wave like this for the particular conditions that we were talking about, a planar diffusion process. And this is similar to the Cottrell case that we solved before, where we did a potential step to a planar diffusion electrode. If we don't have planar diffusion, we would not necessarily see a shape like this peak and then decay. If we had, for example, a rotated disc electrode, which we'll talk about in a chapter or two, those would have a quite different looking wave. Or if we had an electrode that was not a planar diffusion electrode, such as had spherical diffusion, the wave would not have this particular shape. But the majority, by far, electrodes are planar type electrodes, and they will have a shape like this, and so that's what you'd normally see in voltammetry. Now, I got a question from one of my students about why does the shape look like this? Remember, we talked a lot about current potential curves previously, where we plotted the current versus potential, and we showed this nice sigmoidal shape, and somewhat like that. And we put there that there was a limiting current that we could measure, and that we said that that limiting current was a time-independent current. It didn't change with time. But here we see this current is not a steady-state current. If we plot, for example, this current versus the applied potential, which is what is normally done in voltammetry, we get a plot of I versus E, and the graph looks exactly the same as the time curve because the potential is a linear function of time. But here we see a different looking wave. What's the difference? Well, the difference here is that we've assumed in this particular case that we've got a different sort of mass transport than planar diffusion will give us. And so that's the main reason for it. I thought for now what we could do is look at some simulations of the voltammetry process, and we'll see exactly why we expect to see a peak here rather than a nice sigmoidal shape. And in fact, it works out that having a peak here makes the mathematics a little bit more difficult, but it makes the curve a little bit more information rich. You can look at the shape of that peak and how it's shifted along the axis, and whether it's broad or wide, what the height is, and you get a lot of information out of that peak that you don't get out of a nice sigmoidal curve. In principle, both have the same information, but this, your eye can actually see, your brain can process those visual differences easier. Well, cyclic voltammetry is a variation of linear sweep voltammetry in which we just do an experiment and almost everybody will say CV. I did a CV for a cyclic voltammogram or voltammetry, so what was the CV? Did you use CV? What does the CV look like? That's the lingo.